Warm welcome, everybody. Thank you for being here. Get yourself ready. Grab a notebook to write on, pencil or pen. This is math from the void. Math coming at you pretty much out of nowhere. And today we have this continuation of Calc AB practice for response questions. Previously we worked on 3 questions at pace, so within the time limit, and this time we're going to do the non-calculator questions. Same idea, 3 questions, 45-minute strict time limit, but you should really strive for quicker than that because you want to be able to check your work in some capacity. So you don't really need a graphing paper or a graphing notebook for this. You could sketch this graph. What's going on here? It's a typo. This should be a 1. I mean, it's placed properly, but it's just not labeled properly. This should be a 1, 2. I don't even know if that is better as a 1. Let's just scrap this whole coordinate, and I'll just put a point here. This is 1, 2. Okay, there we go. But like I said, you don't really need grid paper. You do need to sketch this out, but if you have the points and just connect them, there should be 3 line segments, and you'll be fine. Right? There's not too much to worry about there. Of course, we have this connecting line segment, and then we have that connection of the line segments. So with these 3 problems, you should strive for about 12 minutes per problem. And as I said, these are non-calculated problems. So you're going to want to make sure that you're able to do the conceptual thinking and explaining. If there are any calculations that you need to do, they're going to be very manageable. Okay, so I'll let you take a look at the 3 questions. Here's the first one. You've already got a chance to see that, and you saw the graph. Here's the next question. First impressions. Implicit differentiation. So when you're solving these, you can just pause the video now, check out this one, and then you can resume and go to the next one when you want to work on the next one. This one is very AP-like. Very, very AP-like indeed. Okay, so as I said, give yourself about, let's say like 35 to 40 minutes is a good pace. Even 13 minutes a problem is fine. It's great. And then when you're ready, come on back and see how we do it here. Alright, let's get started. Part A, and as it says, the function is 3 line segments. Part A, let g be the function that is defined by the integral of this graph from -4 to x. A little bit of typo here. It says for each of these, g of -1, I want you to find that. I want you to find g prime of -1. I want you to find g double prime of -1. Find the value, or, not of, or state that it does not exist. So let's get started with g of -1, shall we? It's pretty easy. G of -1, we're going to find that by using the Fundamental Theorem of Calculus. We can say that g of -1 minus g of, oh, well, really, it's just the integral from -4 to -1 of this graph. So let's go ahead and find that. Pretty straightforward. So from -4 to -1, that is a trapezoid, okay? So just find the area of this trapezoid. We have the basis. This has height -3, and this one has height -2. I guess I should say base has length, and then the height of the trapezoid would be here, because we visualize these trapezoids in calculus as sort of like standing on their sides, like tipped over along their height. Okay, so pretty simple use of the area formula of a trapezoid. Very quick. You should be able to do that very quickly. This is going to be 1/2 base 1 negative 3 base 2 negative 2 times the height, which is 3. Alright, so we have negative 5 times 3 over 2, and you can call that negative 15 over 2. Okay, it makes sense that it's a negative value because we go here, we're only looking at space that's underneath the x-axis, so all of this is going to be negative. Yeah, looks good. Alright, that's one small part. We need to now find g prime of negative 1. So we need to indicate that g prime of x, according to the fundamental theorem of calculus, is going to be d dx of f of x, capital F, that's the antiderivative of f of t, minus f of negative 4. Of course, this is a constant, so this goes to 0. This simply becomes f of x. So the derivative of g is equal to the function value of f, meaning that g prime of negative 1 is simply f of negative 1. Do you remember it? It is negative 2. There we are. Okay, and of course g double prime is therefore the derivative of f. G double prime of negative 1 equals f prime of negative 1, which does not exist. Right? There's no slope at negative 1 because there's a sharp corner there. So there's no tangent slope. In other words, the derivative of this graph is not continuous at x equals negative 1. So those three formulate our answer for part A. Very good. Now there are 4 parts, so we've got to get moving, guys. For the function g given in part A, so same function, find the x-coordinate of each point of inflection of the graph on the interval from negative 4 to 3. Explain your reasoning. So we're actually going to do the explaining first. We're going to say that g double prime, oh, rather I should say g has a point of inflection when g double prime changes sign. And that means that f prime changes sign because g double prime is the same as f prime. So in other words, the slope of the graph changes sign. We can also say the graph f has a relative max or a min. Max slash min. If that happens, then the derivative, then this graph would have had to have gone up to down or down to up somehow, whether it does it smoothly or whether it does it not smoothly. If it's going top of a hill or bottom of a valley, that means the derivative is changing sign. So if we just look at the graph, when does its slope change sign? Here we're going positive slope, right? Positive slope, and then we still make a positive slope. We bend all of a sudden, but it's still positive slope. And then we go negative slope. So here at x equals 1 is the interesting, yeah, that screwed up point. That accidentally had the wrong number there. At x equals 1 is when we have that point of inflection. We can say f prime goes positive, negative. So that means g double prime changes sign. Yep. Okay. Part C. Let h be the function defined by, the integral from x to 3. A little bit different now when we take the derivative. Find all values of x in the closed interval such that h of x equals 0. Okay, so what we're going to want to kind of do is we're going to kind of want to sort of go backwards almost on this function f from 3. And if we go backwards and see where we have the same area, then we know that the integral is going to be equal to 0. Here's what I mean. We want to find where is h of x 0, meaning where is the integral from the starting point up to 3. Like if I wanted to choose x to be from here, then I would be taking this negative space plus this space plus this space. That needs to equal 0. Got it? So the integral from that point, x, that I start at, all the way to 3. So if we work backwards from 3, I mean, of course, actually, the first answer is going to be 3. X equals 3 for sure, because the integral from 3 to 3, we're on this closed interval. From 3 to 3 is definitely an integral value of 0, if you're not moving at all. But from there, let's go backwards. So here we have this. That's all negative. That's a triangle. So if we start at 2, from 2 to 3, we're just going to get this negative triangle space. But if we go back a little bit more, if we go back to 1, then that from 1 to 3 will balance out and will be 0. Because this positive space will cancel out that negative value. So x equals 1 is also a solution. All right, let's keep making our way backwards. So now we're balanced again at 0. But if we keep going backwards, we're adding more, another triangle. And then we start going backwards. Let's look at negative 1. We have a negative value of triangle, or a triangle of negative value, which is equivalent and opposite to this triangle of positive value that we just added from 0 to 1 while we were going backwards. So that means also at negative 1. Now if we try to back the x up even further, since we're currently at 0, this is just going to be contributing negative area, or negative value. So we're not going to have any other solutions up to negative 4. All right, but that's how we would break that down. So I'm going to erase this just because I might need this graph for other stuff in a moment. But that is logic. Okay, so those are the only 3 values. Part D, for the function in part C, so h, this integral from x to 3, find all the intervals on which h is decreasing. Let's use our translation devices. What does that mean? What does it mean for h to be decreasing? That means h prime is negative. Well, h prime is the derivative of h, which means it's the derivative of the integral from x to 3, which means we use the second fundamental theorem of calculus, and we say it's the derivative of capital F of 3 minus capital F of x, which means this constant f of 3 goes to 0, but then we end up with negative f of x. Again, we need this to be negative, which means we need f of x to actually be positive. So this is the explanation of the reasoning. A lot of times we use the given information, the fact that h is decreasing, we use that to derive some other truth. And that other truth is going to be easier for us to spot. In fact, we just have to look on the graph when it's positive. So that's going to go from 0 to 2 inclusive. Not inclusive. If you wonder why it's not inclusive, f of x has to be greater than 0. Is it greater than 0 at x equals 0? No, it's equal to 0. Is it greater than 0 at x equals 2? No, it's greater than 2. So that does it for the first question. Let's move on to the next. Got some implicit differentiation vibes. I think I mentioned that earlier. Given the curve y squared equals 2 plus xy. Now that's a pretty gentle implicit curve that they've given you. I would say this is probably like 75% intensity, compared to the AP exam. That being said, it seems appropriate because this is a non-calculator section, but also there are 4 parts. So sometimes they make the derivative part a little bit easier if they're going to ask you a lot of questions about it. If there were only 3 parts, it might have been a slightly tougher derivative. But the questions that they're asking, they are very, very good AP level questions. So I just mean this equation is not that intense. But the overall question, I think, is designed really well. They will often do this for part A, tell you to show that dy dx is equal to this. That's what really gives it away that it's an implicit differentiation problem, if it weren't already clear. So we're going to want to take a derivative of both sides, but you see that there's a y in both sides. So yeah, it's going to turn to dy dx situation. Let's go ahead and do the derivative of the left side is 2y dy dx equals derivative of 2 is 0, plus we have a product here. How do we do a product? We take a derivative of the first thing, leave the second, plus we leave the first thing and take a derivative of the second. So we're just going to have 1y plus x and then derivative of y dy dx. So let's get all the dy dx stuff by itself. Let's move all the dy dx stuff to the left side. So that's going to leave us with dy dx, and the pieces that have it are 2y plus x. This equals to y, which means dy dx is just y over, which is exactly what we're expecting to get. Oops. With a minus, of course, because I subtracted it to the other side. So this is what we're expecting to get. Very easy part A. They're kind of basically showing you what you need to end up with too, which is pretty convenient. Okay, easy enough. Part B. Find all the points on the curve where the line tangent to the curve has slope of 1/2. So again, I'm going to teach you guys how to interpret these phrases. When they say where or that, that are related, or when they say, they used one on the last problem too. Where was it? It's when they use, on which, for which. So this one here. Find all the intervals on which. That's a transition phrase. That's letting you know that you can take this as an assumption and use it, and then do some logic with it and get some kind of result that you can observe. So where the line tangent to the curve has slope 1/2, that means we can assume now that this is equal to dy dx. We can assume that this is equal to the slope of the tangent. Slope of the curve, which is the slope of the tangent at that point. Okay, so if we assume that that's true, let's set this equal. Let's say y over 2y minus x equals 1/2. And what's the goal here, by the way? We want to find all the points. So our answers need to be in terms of like x comma y. All right, that's when we're done with the problem. We have a bunch of x comma y's that have that 1/2 slope. So let's just kind of solve and work through this equation. Cross multiply. You get that 2y equals 2y minus x. Well, that's pretty easy. That means we subtract 2y on both sides. 0 equals negative x, or in other words, just 0 equals x. Now, that's not a point. That's an x value. We get to use this now, somehow use this clue to find points. How do we find points? We use the original graph. The original function, that is. I mean, it's not a function. The original equation. So we have y squared equals 2 plus 0 times y is just 0. So here we go. We can solve this, and do not forget, do not forget, when you're solving an equation by taking a square root, you must use plus or minus. Goodness me. So the points are 0, comma square root of 2, and 0, comma negative square root of 2. Bam. Done. Okay, let's look at this. Show that there are no points. They just want us to show there are no points on the curve where the line tangent to the curve is horizontal. That's a key phrase. They're telling you, go ahead and assume that the line is horizontal and show that there are no points, which means you're going to get some kind of false statement about the points, or you're just going to get no solution on the points somehow. But let's talk about what this means. Horizontal. What does that mean? Horizontal means dy dx equals 0. We could assume that. If that's true, then we can say for sure that y over 2y minus x equals to 0. And if that's true, multiply both sides by the denominator, or if you just understand that a fraction is equal to 0 when its numerator is equal to 0, that says y equals 0. Now, if that were true, we would be able to find points. Kind of the same process that we did in part B, but with the y's instead. Find points. We're not going to find any points, of course. We're trying to show that there are no points, so hopefully we'll reach some kind of contradiction. 0 squared equals 2 plus x times 0. 0 equals 2. Well, that's obviously not true. So then this is not true, so then this is not true, so then this is not true. You get the idea. No solution. Therefore, we have shown that if we take the assumption of, yeah, this thing goes horizontal at some point, we're not going to find any points that go along with that. Okay? All right, done. Let's look at part D. Question D says, let x and y be functions of time. Interesting. That are related by the equation. Okay, same equation. At time t equals 5, this is almost like a related rate portion. At time t equals 5, the y value is 3, and dy dt is 6. Find the value of dx dt at time t equals 5. So like under the same conditions, that means that, when y is 3 and when dy dt is 6, okay? So what we have to do here is we have to take derivative of both sides, but we have to do it with respect to time, which means that we're going to get an implicit derivative on any variable, the x and the y. Here's what that looks like. 2y dy dt equals still 0, derivative of 2 is still 0, plus here's our product. So remember how we do the product. It's going to be derivative of the first thing, leave the second thing alone, plus leave the first thing alone, take the derivative of the second thing. So that's going to be dx dt times y plus x times dy dt. Now we have some values for everything, so we can plug in, but we do not have a value for the x. So let's go ahead and find that using the initial conditions. How do we find an x? Using the condition of y equals 3. Well, we can just say that 3 squared equals 2 plus x times 3, or 3x. So 7 equals 3x. So 7 over 3 equals x. And now we have all the information we need. We have y is 3, dy dt is 6, x is 7/3. Let's go ahead and solve. You don't have to isolate the dx dt if you don't want to. You could just plug things in and everything else will just fall into place. So 2 times 3 times 6 equals this thing we're looking for, times 3, plus we determined that x is 7/3, and again dy dt is 6. So that's kind of nice. It's times 2. So this is 14 equals 36 3 dx dt. So 22 over 3 is our dx dt. Very interesting part of the problem there at the end. We had to do basically a related rates situation. They just sprinkled in a little bit of related rates to the end of that question. All right, let's move on. I think we're making pretty good time. Move on to number 6 now. All right, let f be the function defined, and this is very AP-like. Like this problem is 100% like a free response problem. Let f be this function defined by a piecewise function. So natural question is this piecewise function connected? Well, it's potentially not connected at 3, even though there is a function value at 3 defined by the top piece. How do we determine if it's continuous? Which is actually the question for part A. Okay, well, cool. I was going to go through that anyway. Is f continuous? That's the assumption that we're making. Is it continuous? Explain why or why not. Well, we'll do the explaining first, and that's going to motivate how we come about our process for determining. It's continuous if f of 3 equals the limit as x goes to 3. That's how we'll know it's continuous. So we need to determine if the limit exists, which means we need to determine if the left and the right go to the same place. So x goes to 3 from the left. That's going to be the same thing as using the top piece. Square root of x plus 1, which is just the square root of 4, and so that's just 2. Now the piece on the right, limit as x goes to 3 from the right, that's going to be the same as the limit as x goes to 3 from the right of, I guess I should just say 3 on both of these. Since we're already using the one-sided function, we can just drop the one side away. This is just going to be 5 minus x, 5 minus 3, which is 2. So the left and the right sides match. And of course, the function value itself is just equal to this on the right side. So the limit as x goes to 3 is equal to 2, which is also equal to f3. So it's continuous. Very easy to get part A. You could even just write that the function needs to equal the limit, and you probably get 1 point. You get another point for actually showing whether or not it is. You're just like, it's continuous if this is true. And if not, it's not continuous. That gets you a point. Part B. Find the average value on the closed interval. So that's prompting you to do kind of a formula here. So the average value formula with integrals is going to be 1 over b minus a times integral of a to b f of x. Some people just put it on top. That works too. This is going to be over 5 in this case. It's the same as finding an average, right? You add up all the values, that's what an integral does, and then you divide by the number of values. Well, in this case, it's the size of the interval, because we're using continuous values. Okay, the thing is, this thing is 2 different functions, so we're going to have to take this integral piece by piece. We're going to have to do this from 0 to 3, and then we're going to be able to do this from 3 to 5. So this is going to be 1/5 times the integral from 0 to 3, square root of x plus 1 dx, plus integral from 3 to 5 of 5 minus x dx. Okay, very easy to do. This is the same thing as like a 1/2 power, right? This is x plus 1 to the 1/2 power. And it doesn't really require a u sub necessarily. You can just raise the power and divide by the new power. Because the du would not be anything interesting. If we did this as a u sub, du would just be dx. So it doesn't do much. Let's see, this is going to be 2/3 x plus 1 to the 3 halves which we can just go ahead and call the square root of x plus 1, and then cubed. That's going to go from 0 to 3, but then we're going to add this antiderivative. Don't take the 2/3 out, because they don't, only this thing has the 2/3. The next term that I'm going to write does not have a 2/3. In fact, let's put that in there. Plus 5x minus x squared over 2, and this is going to go from 3 to 5. So if we can evaluate all that, that's all we need to do. Very direct. See how our work just flows straight from there. All right, now let's plug in 3. It's very easy to do that. If you plug in 3, you just get the square root of 4, which is 2. 2 cubed is 8, so we get 16 on 3. And then if you plug in 0, you get square root of 1 is 1, 1 cubed is 1. 1 times 2/3 is, of course, 2/3. Now we're going to add to that this other integral that we have to evaluate. We've already taken the antiderivative, but we have to evaluate. Plug in a 5, so you get 25 minus 25 over 2. So 25 over half of 25 just leaves us with half of 25. And if we plug in 3, what do you get there? 5 times 3, 15 minus 3 squared over 2, that's 9 over 2. I guess we could just call 15 30 over 2. So we have 30 over 2 minus 9 over 2. That leaves us with 21 over 2. Okay, we're just working our way, through it. We have 14/3 plus, what is this, 4 over 2? So that's just 2. We can call 2 6/3. Why don't we? So this is going to be 1/5 times 20/3, cancel the 20 and the 5. We get a result of 4/3. That's the average value of the function. It kind of makes sense. I mean, if you think about what those functions look like. Square root of x plus 1 technically starts here at 0. And then we have 5 minus x, which is like doing that kind of a thing. So this happens at 1. This trade-off happens at 2. Technically 3, 2. So yeah, it seems reasonable that the average value is like right here. That rectangle should approximate the entire area. It's reasonable. Not that we had to show all that, but it's a little gift for you. Part C. Let's look at part C. Final part of this final problem, but this will be, a little bit labor intensive. Suppose that g is a function very similarly defined, but not exactly the same defined. It's some multiple k times x plus 1 in the root, so that's like this thing, but like multiplied by some k. And then we have a different linear equation from 3 to 5. So the question is, if k and m are constants, and if, that's another assuming word, go ahead and assume if g is differentiable, what are the values of k and m? So we get to use this fact, g is differentiable. That means that it's continuous. If we know that it's differentiable, then we know it's definitely connected. Because you can't have a differentiable means it has a derivative, it has a tangent slope. You can't have a tangent slope if you don't have a connected graph. So it definitely is continuous. What does continuous mean? We looked at that in part A. Continuous means that the limit as x goes to 3 from the left of g of x, which is needs to be equal to the limit as x goes to 3 from the right of g of x. Which means that, that's what was confusing me. A lot of typos on this one. This is g of x, it's more appropriate. Suppose that g is the function defined by this. So let's figure out what is the limit as x goes to 3 from the left. Even though there's this k which we don't know, we can still figure out what it comes out to in terms of k by plugging in to 3. So this is going to be the limit as x goes to 3 of k times square root of x plus 1. I could really just take the k out of it. But if you put in 3, that's just going to give you 2k. Meanwhile, over here, we have that this is equal to the limit as x goes to 3 of mx plus 2, which means this is equal to 3m plus 2. Okay, I'm kind of stuck here because we only have one equation, but we have two variables. We can imagine different values, but let's not do that. Let's just actually solve this because we have another thing that results from our assumption. If we assume it's differentiable, that means that the derivative exists. I guess I should say smooth. It's continuous and it's smooth. Alright, so what does that mean? That means that the left and the right side derivatives also match. So the limit as x goes to 3 from the left of g prime needs to equal the limit as x goes to 3 from the right of g prime. Let's work with the right side first, because that's going to be the limit as x goes to 3 of the derivative of mx plus 2, which is just m. So that just equals m. Alright, that's nice. That means if we can get the derivative on the left side, we're going to be good to go. So what is g prime? Well, since g of x, let's get a really clear definition of this piece of g of x. This is really equal to k times x plus 1 to the 1/2. So therefore g prime is going to look something like this. 1/2 times k, x plus 1 to the minus 1/2. And then you would theoretically use the chain rule inside, but the derivative of that inside is just 1, so there's nothing really to consider there. We could rewrite this as k over 2 square root of x plus 1, which I'm going to do here. So then the limit as x goes to 3 of that that's just going to be k over 2 times 2, which is k over 4. And these are equal. So if m equals k over 4, we can say 4m equals k. Now it's time to use this fact and plug it into our model over here. That means that 2 times 4m, which is 8m, is equals to 3m plus 2. And that means that 5m is equal to 2. So m equals 2 over 5, which means that k equals 8 over 5, because 4 times that. Alright. Nice and smooth and easy. Now this would be an amazing time to go back and check your calculations. Make sure they seem reasonable. I did a couple little sketches here and there to see if things seemed reasonable. Like if you have any equations, just go through the equation again. You're like, did I do that right? Cross multiply 2y minus x, 2 times y, subtract. Yep, looks good. You know, just checking some stuff. Make sure you did the product rule correctly. You don't have to check all of the plugging in, but make sure you did the product rule correctly, because if that part's wrong, you can pretty much guarantee your answer is going to be wrong, right? So just checking the setup to make sure you're using the assumptions properly. And if it ever says unit, this is a great time to go back and check for when it says like indicate units of measure. If it does, nothing like on these questions did. And that's what you can expect from non-calculator free response question. Is they're going to have you do some light calculations, right? We had to do some light calculations. Look, we had to, subtract 2, divide both sides by 3, divide by 3 here. Even on this integral problem, we did have to plug some stuff in. So that was probably the most computation-heavy portion of this entire video. Was part B and part C of this problem, because we had to actually take derivatives by hand, You know what I mean? Whereas this had a little product rule, and this one we didn't even really have to take a derivative. We just sort of theoretically took a derivative, right? We took the derivative of an integral, which just turns into the function, and then we took a derivative of that, which is the slope. So we just used our eyes on this graph because it gave us a visual representation. Okay, that's the recap. If you need to check anything, go back to the video, go back to the part where I checked it. I try to chapter these things pretty well for you guys, so that you can navigate it and not have to just like stare through and wonder when do we get into the next part, or even get a preview on what's going to be discussed. All right, keep studying. Don't stop studying. I know you probably have other classes too to worry about, but I'm here for your math support. That's enough blab out of me. See you guys next time in the void.